Thank you, Bernard, so much for coming on the podcast. It's such a pleasure to see you. I always love to connect with you, to converse with you. It enriches my life every time that we do that.
Thank you so much, Arabella. And the feeling is mutual.
Sorry?
The feeling is mutual.
Oh, well, that's very kind. Yeah, I'm particularly excited for today's discussion. Let's get straight in there, yeah? And begin with talking about time, the meaning of time, specifically how science currently understands time. And I'd love it if you could describe how the dominant paradigm, which is the materialist paradigm, particularly the thermodynamic arrow of time, frames our experience of temporality.
Okay. First of all, I should explain I am a physicist, I'm a cosmologist, and I'm going to answer your question from the perspective of physics. Now, the original view of time was the one which is associated with Newton 300 years ago, which says that time is absolute, it's the same everywhere, and it's the time measured by clocks. And so all observers agree about time measurements and space measurements and things like that. But of course, all of that changed at the beginning of the 20th century when Einstein came along with his theory of special relativity. And what he showed was actually time is like a fourth dimension. And you have to merge the three dimensions of space with the one dimension of time to form what is called space-time. And that really completely changes our view of time. And it means that, for example, moving observers will measure different time. So moving clocks run slow. And because of that, you get the so-called twin paradox, where one twin goes off close to the speed of light and comes back to Earth, and he's only aged 1 year and his twin has aged 1,000 years or something like that. So the view of time, which comes from modern physics, from relativity theory, is that time is not absolute. There is no absolute present. Not everyone agrees on time observation. Not all clocks agree. But nevertheless, this beautifully unifies how we all observe the world. I mean, the difference from Newtonian theory only arises when you start moving close to the speed of light. But nevertheless, it's a huge conceptual change because it demolishes our common sense view of time. But now you also referred to the thermodynamic arrow of time.
Yeah.
Well, actually, that idea goes back before relativity and can really be discussed in Newtonian terms. The point is that within physics, there are various arrows of time. And, for example, there is a causal arrow. The cause comes before the effect. Okay, so you can smash an egg to make an omelette, but you can't undo the omelette to make the original egg. Then there is the time associated with, for example, the expansion of the universe. Okay, the universe is expanding, so there is a difference between the past and the future, because the point is that most of the equations of physics are time symmetric. You can replace t by minus t. In practice, though, we know that the various time asymmetries arise. In electromagnetism, for example, we know that there is a distinction between what are called advanced waves and retarded electromagnetic waves. One propagates into the future, okay, and one comes from the past. So a lot of interest in physics arises on that distinction between advanced and retarded. I suppose also, of course, the other direction of time is that we're all aware of is the passing of time. Maybe the most famous arrow of time is the so-called entropic arrow of time. Now, the second law of thermodynamics says that entropy increases with time, which in some sense means that the universe becomes more distorted. Right. You can get pockets of order where things become more ordered and you get more complex systems, but overall, entropy must always increase. And so that's the arrow of time which most physicists think is most fundamental. And indeed, ultimately, most people would argue that all those other arrows of time probably relate to the thermodynamic arrow of time, which says that entropy always tends to increase. But then that, of course, raises the question of why it always increases. Yeah. And there's been a lot of discussion about that. But the argument most people like is that it increases because the universe started in a state of very low entropy. In other words, at the Big Bang, because we think the universe began with a Big Bang 14 billion years ago, that must have been in a very low entropic state. In other words, it started with a very low entropy. This is sometimes called the past hypothesis.
When you talk about more entropy, just for the listeners, what do you mean by that in a couple of sentences?
Entropy, if you like, is a measure of disorder. So in other words, you may start off with a cup, which, okay,
Yeah.
then I smashed the cup on the ground, and that has actually smashed it up, and it's increased disorder. So the second law of thermodynamics says that on average, that the disorder in the universe must increase. And this gave rise to the idea in the 19th century of that heat death, that eventually the universe has to run down so life would disappear. However, that's true globally, but it neglects the fact that you can have little packets where the order increases.
The microstates.
I'm talking here not so much about microstates, but individual people, for example, or any level of organization involves increasing order, and life in particular involves some increasing order.
Yeah.
But that doesn't contradict the second law of thermodynamics, because globally the net disorder is increasing, but it's just that you're getting these pockets of increased order. And that's the crucial difference between, if you like, 19th century thought and 20th century thought. We now allow for the fact that you can have order, and in particular life, arising and maybe persisting indefinitely, whereas in the 19th century one had the view that the universe was running down. So that was an important conceptual change.
I think it's also important to understand in terms of time, because I wanted to ask you the more abstract question of what time is. And we don't need to go too far into that because that's actually a really big question. But just in terms of entropy, because entropy is also, it's not only the movement from order to disorder, it's also the movement from heat to cold. It's heat dissipating itself, correct?
Yeah.
Yeah. So for example, the sun as a star burns itself off, yeah, which is this heat death you talk about. This is the movement of energy, all that light and this energy and this heat, as it burns itself off, it's moving. It's moving in one direction as it burns itself off. And that's what's allowing all these states to, like, carbon-based life, right? Like all of these complex systems of a solar system and all of that stuff to emerge around it. And it creates time, whatever time is, that's what creates time, yeah? Our sense of time is governed by the sun, the earth is revolving its axis, and that creates days, right? And that's where we get our sense of time. Like, are you following what I'm saying?
It is, of course, true that our sense of time is governed by all sorts of natural processes, in particular astronomical processes. So when we talk about days, we're talking about the rotation of the earth. When we're talking about months, we're talking about the rotation of the sun around the earth. When we talk about years, we're talking about our motion around the sun. So there is a link, of course, between our time and our measurement of time and astronomical measurement. The concept of entropy, that's a more subtle link, because that's talking about defining a direction of time.
Yeah.
And so, for example, the term heat death wasn't specifically referring to the sun dying, it's referring to the whole universe.
When the sun dies, though, it'll go through its own heat death, right?
All forms of structure tend to eventually dissolve. And that is also a manifestation of the second law of thermodynamics. But so the second law of thermodynamics does define a direction of time, but of course the concept of time itself preceded that.
So what is time then? What is it?
There are different sorts of time. When a physicist talks about time, one is talking about what you would call chronos. It's something which can be quantified. It's something which can be measured by clocks. Something objective. And so when I'm talking about time, I'm talking so far from the perspective of a physicist.
Yes.
Now, when you ask what is time, you're really asking a much more general question, which really relates to the theme of these talks. I mean, it relates to Kairos. And that's a deeper question, which relates to our experience of time, because the other arrow of time is the psychological arrow of time. We'll come back to that later. And that's to do with consciousness.
Okay.
And so that is a topic which is not addressed by the current physics.
No.
But I will argue that physics should expand to accommodate it. And so when you ask the question, what is time? I think you're really hinting at the second question.
I'm also interested, sorry to interrupt you, I'm also interested what a conventional, because your career has been within the academy of conventional cosmology and so on, even though you have more expanded ideas, which you've been able to expand, especially since you kind of retired from the mainstream academy, what would a quote unquote conventional cosmologist say time is? What would they say time is?
Cosmology is part of physics. So a conventional cosmologist would think of time in terms of the relativity theory.
Okay.
But a little bit more subtle than that, though, because actually Einstein introduced special relativity, and that's where you get this view of space-time. But then he went on to talk about general relativity, which is his description of gravity. And in general relativity, space-time, if you might think of space-time as a flat sheet of paper, in general relativity, the space-time is curved. The sheet of paper, if you like, is curved by the presence of matter and energy. And that modifies your view of time still further. Okay. And I can say a little bit about how general relativity modifies your view of time, if you like.
Yeah, I'd love that. And that beautifully segues us onto the next question about what gravity is as well.
Okay. And of course, general relativity is about gravity.
Perfect.
So talking about then Einstein's theory of gravity, which it says it's due to curved space-time, this also modifies time. Now, I explained how in special relativity, clocks run slow if they move, and the faster they move, the slower the clocks run. In fact, if a clock moves at the speed of light, it basically doesn't change at all. It doesn't register time at all. But another effect comes in general relativity due to the fact that space-time is curved. That means that both space and time measurements get changed. And what you find is that actually time slows down in a gravitational field. Okay, now it's normally quite a small effect, but it's an effect which has been measured. So in other words, if you take a clock which is further away from the center of the Earth than an object, say, on the surface of the Earth, the gravitational field is weaker. So therefore, the clock, which is further away, goes actually faster than the clock which is on the surface. And that effect has been measured. Okay, it's been measured by experiments. What people do is they fly atomic clocks in planes. And that's quite clever because you're actually measuring both the effect of the speed, which is special relativity, and the effect of the gravitational field. So clocks, if they're in an aeroplane, they're actually going to be running a little bit faster because the gravitational field is weaker. It's further from the center of the Earth. And those experiments, they're called the Haffel-Keating experiments, they confirm both effects. So we now know that the effects of gravity on time and the effect of speed on time are correct as predicted by relativity theory. And so that is confirmed. And that changes our view of time even more. And so I'm now describing the view of time which comes from general relativity. Yeah. But now you talk about cosmology, you introduce the fact that I'm a cosmologist. Now, in cosmology, the point to realize is that we can only understand cosmology and the expansion of the universe in terms of general relativity theory. The whole point about general relativity is that it provided a proper mathematical basis for understanding the whole universe.
Okay.
In particular, Einstein's theory predicted that the universe should be expanding. Einstein didn't realize it at the time. He thought the universe was static because in 1915, we didn't know about other galaxies. And 1915
really?
No, Einstein's relativity theory was in 1915. At that time, most people thought the galaxy was the universe.
Wow, I didn't know that. That's amazing. I mean, that's only a century ago.
Well, and then it was only 15 years later that Hubble discovered that there were actually other galaxies outside our own galaxy. And furthermore, all these galaxies were moving away from us. They were expanding. Right. Why we understand that in terms of relativity theory, because relativity theory predicts that space itself is expanding. So I told you, you can think of space-time. Well, you can think of space as a surface of a balloon. And in some sense, space is curved. And when you blow up the balloon, the galaxies move further away from each other. So Einstein's theory predicted the cosmic expansion. But at the time, Einstein didn't realize it. In fact, it was somebody else called Friedmann and then someone called Lemaitre who actually realized this. Einstein himself didn't believe at first that there was anything outside the galaxy. So he missed the big opportunity to predict the expansion of the universe. But anyway, the point is that once you've got a cosmological model, that itself provides a form of time. because the expansion of the universe is amazingly smooth, but we think everywhere all the clocks are going to be measuring the same time.
Yeah.
And so the expansion of the universe itself provides a sort of time.
Yeah.
Because you see, in relativity theory, time in special relativity, time is not absolute. Different clocks measure different rates, if you like. But what's interesting is that in general relativity, it's even more complicated, and clocks measure different rates because of the gravitational field as well as because of their speeds. However, the irony is that when you look at the universe as a whole, it's remarkably smooth. That means that it defines very special clocks, which in some sense are co-moving with the universe, and they all measure the same time.
Yeah.
So in general relativity, you predict the existence of what is called cosmic time, okay, which is the time associated with the Big Bang. In other words, with the expansion from the Big Bang.
How does gravity play into this? We know it slows time right down. What is gravity? I've asked you what time is, and you've done an amazing job of answering that. Certainly before we expand it with consciousness and so on. What's gravity?
For Newton, gravity was a force, simply a force between two objects, but he couldn't explain where that force came from.
Okay.
In Einstein's theory of general relativity, I explained that space and time are curved, and gravity is no longer a force. Now, the way you can look at this, and the picture you often have, you imagine space, okay? You imagine space is like a sheet of elastic, and you put some object in the middle of it, and the sheet of elastic sort of sinks in the middle, so the sheet is curved. And what that means is that objects nearby actually naturally follow certain trajectories, like being in orbits. But that is not so much because there is a force, it's simply because the central object, the sun, for example, has curved space, and objects merely move, in some sense, in the shortest distance in this curved space. But the shortest distance, what's called a geodesic, that corresponds, for example, to the Earth moving around the sun in an orbit. So that's how Einstein has explained gravity. And that curvature also is producing modification in clocks. And so there is a link between clocks, the clock rate, and between the gravitational field. And in fact, gravity always tends to make you move to where clocks run slowest.
Do you think there's a deeper metaphysical dimension to gravity?
That's interesting. It depends what you mean by metaphysical, because every theory has a metaphysical aspect to it, and relativity theory certainly has a metaphysical superstructure, if you like. But it raises a particularly interesting question, because if you're talking about the curvature of space, you naturally ask, well, what's it curved in? You know, I gave this image of space as being like an elastic sheet which is being curved. And I didn't say, what is it curved in? Right. Well, actually, that curvature, it's curved in an extra dimension, but it's not curved in time in this case, because it's, in some sense, this curvature seems to make reference to a higher dimension. Okay. Now, the point is that most relativists will say that doesn't mean there really is a higher dimensional space. It's just a mathematical way of describing what we call the metric of space-time, which can be interpreted as embedding space-time in this higher dimensional space. But most relativists will say, but it's not, doesn't mean the higher dimensional space is real. However, I'm actually going to argue that in some sense that embedding space in relativity may be real. And indeed, the idea of higher dimensional spaces is going to arise in other approaches to physics, from various attempts to unify the forces, M theory and things like that. I do think that the question of whether Einstein's theory of general relativity raises a deeper metaphysical issue is a very relevant question, because the question is this higher dimensional embedding space, which you use to describe gravity, is that in some sense physically real, or is it just a mathematical device to describe it? And I think we'll come on to that later on in our discussion. But I mean, the standard relativist answer will be, well, it doesn't have metaphysical aspects because physicists aren't interested in metaphysics.
I've made a note of mathematics because I do want to come back to that and think in terms of pure mathematics, because from what I understand, a lot of pure mathematics, which is really just the exploration of mathematics as a pure form, a formal expression of truth, that it can sometimes be centuries before a discovery in pure mathematics then becomes applied.
There's an intimate link between physics and mathematics. Basically, all our models of physics have to be expressed in terms of mathematics.
Yeah.
But this gives rise to a bit of a controversy, even among physicists, about what counts as physics. Is it real if it's mathematics, or distinction between physics, mathematics, and reality? And all these things are linked. And so, for example, we might talk later about M theory, this attempt to unify the forces. It's very complicated mathematically. There's still no empirical evidence. So some physicists, more conservative physicists, will say, well, this isn't physics, this is just mathematics. However, the fact of the matter is that most of physics is mathematics, and it's just that sometimes the math goes beyond the physics, so you have to wait 100 years before you realize that there's application in physics. But sometimes the physics goes beyond the mathematics, so you've got some idea and it has to wait for the maths to catch up. So it goes in both directions, but the link between maths and physics is fascinating.
We can come back to that as well if we talk about the Wick rotation, which I would like to at least briefly, and the number I and imaginary numbers. We could come back to that. Before we go there, I would like to touch on very briefly light. I have a special fascination with light, and it is relevant to a discussion on time since photons are essentially timeless. So I was going to ask you about the role that light plays in shaping the fabric of reality, shaping our understanding of time, how light interfaces with time. And then the kind of polar opposite of light, which is a black hole, which is something that you explored very deeply in your career. Your career sort of revolved around black holes. So if we could talk a little bit about light's interface with time, and then black holes.
That's enough to be getting on with. First of all, light plays a crucial role in relativity theory. Of course, the point is that light travels at a finite speed, 186,000 miles per second. And it plays a crucial role, and Newton knew that, of course. They measured the speed of light quite early on. But the point about relativity theory is that light plays an even more crucial role. And the reason for this is that although people may move with different speeds, everybody measures light moving with the same speed. Now, this is counterintuitive because people used to assume that light would travel with this finite speed with respect to what's called the ether. And therefore, if an object like the planet Earth was moving with respect to this ether, they should measure a different speed for light. But then they tried to find this with what was called the Michelson-Morley experiment at the end of the 19th century. They couldn't find any difference. So people were puzzled by that. But then Einstein came along and said, everybody has to measure the same speed for light. And this is because what you mean by your space and your time measurements have changed. One of the predictions of relativity, special relativity theory, is that if you move with a speed, your measurement of time and space changes, and it changes in such a way that everybody measures the same speed of light. That was counterintuitive. It went against the common sense Newtonian view, but Einstein took that at the starting point, and it was backed up by this famous Michelson-Morley experiment. And furthermore, it was the only natural way to interpret Maxwell's equations of electromagnetism. Okay. The point is, in relativity theory, light plays this crucial role. And you have what is called the light cone, which I'll try and explain. If you imagine, you see, it's rather hard to imagine 4 dimensions, but you can imagine 3 dimensions. So if we imagine that space is 2-dimensional and that time is 1-dimensional, light in some sense travels at 45 degrees in a space-time diagram, okay, because your units of time are multiplied by the speed of light. And so if you draw a space-time diagram, you have what's called the light cone. You've got the future light cone, which is the region for all those events are in the future. You have the past light cone, where all events are in the past.
Yeah.
And then you have outside the light cone, you have what's called elsewhere. And there's ambiguity about the order of events and things like that.
And it
But
looks like an hourglass, doesn't it?
it does look like an hourglass, although it's a measurement of time itself.
No,
but
I know. But like two inverted triangles, if people want to visualize what does a light
exactly,
cone.
it's like that. It's like,
Yeah, okay.
but the point is, light rays themselves travel along this light cone. So they travel at 45 degrees. And so it's a cone because I'm imagining it in 3 dimensions. You can make it even simpler by putting it in 2 dimensions, if you like, and then it's just 2 lines at 45 degrees. So the point is, light cones are absolutely crucial because that is the basis, really, of all relativity. So it all hinges on what that speed of light is, and it's supposed to be the same for all observers. Now you ask about black holes, and you're saying they're the polar opposite. They're not exactly the polar opposite. They're linking very crucially to the behavior of light cones. Now, the point is, what is a black hole? Well, a black hole, you have a region. A spherical object like the Earth, for example, has a gravitational field. It's a spheric symmetric gravitational field. And the gravitational field on the surface of the Earth isn't too strong. It ties us to the surface of the Earth. It takes a bit of effort to go into space and to go into orbit. But basically, the field isn't that strong. However, if you made the Earth smaller and smaller and smaller, the gravitational field will get stronger and stronger. And eventually, if the Earth got compressed to the size of about a centimeter, very, very small, the gravitational field becomes so strong that not even light can escape. You see, there's something called the escape velocity. If you're sitting on the surface of the Earth, the escape speed is the speed you need to get away from the gravitational field of the Earth, to get to infinity. That's called the escape speed.
Okay.
But that's quite low. But by the time the Earth is being compressed to a centimeter, the escape velocity is the speed of light. And that means that not even light can escape from the surface of the Earth. Now, it might be a little bit better to talk about the sun, because actually the Earth will never become a black hole. The sun, that has to be compressed to something like 3 kilometers. And then
how big is it now? How many kilometers is it now?
Oh, well, it's 10 to the 5th kilometers, so it's 100,000 kilometers.
From 100,000 down to about 3, that kind of compression. And very quickly, what is it about the compression that increases the gravitational force, the density?
Well, it's the force is G times m over r squared. Okay, G is the gravitational constant, m is the mass, r is the radius. As the r goes down, so the gravitational force goes up. Like
it's a law of physics. That's just how it works.
Yeah, it's just 1 over r squared. And so that's why the gravitational field gets stronger. So the point is, though, that when you get, and this is a Newtonian discussion, when an object gets too small, the escape speed of light. So light can't escape. Now, according to relativity, nothing can go faster than the speed of light. In fact, we talked about the light cone. What I should have mentioned is that every object has to move within the light cone. It has to be within the future light cone, which means it can never go faster than the speed of light.
Okay.
Now,
yes.
So if light can't escape, that's why it's black. Nothing can escape. Now, of course, all of this is assuming that the object can get to that stage. Now, even Einstein was rather skeptical about black holes. I mean, when he produced his theory in 1916, there was no actual evidence that black holes could exist. But it was realized from a theoretical perspective that they could exist. And actually, eventually, it was in the 1960s we started getting evidence that they do exist. And now there is incontrovertible evidence for certain types of black holes. For example, the sun itself won't become a black hole, but somewhat bigger stars, we know they will collapse, the black holes. Eventually they collapse. They might explode a supernova, but other circumstances they collapse and they form black holes. And we know even with our own galaxy, there may be 1 billion black holes which are stellar remnants. So we know for sure that, and in fact, we've seen these black holes because we've seen their merging black holes through the gravitational wave detectors over the last few years. So we know now, indisputably, that stellar black holes exist. Also, we know there are very massive black holes in the middle of the galaxies.
Okay.
These aren't stars, they're too big for that. Our Milky Way contains a black hole of 4 million solar masses in the middle.
Jesus. Is that a supermassive black hole?
That's called a supermassive black hole. We now think most galaxies have got supermassive black holes in the middle. There's a billion solar mass black hole in the center of a galaxy called M87.
A billion suns.
Billion. And we've seen that through the what's called the Event Horizon Telescope. And so we know for sure black holes do exist. And therefore, this isn't just a theoretical prediction. There are real astrophysical situations where this arises. But it's important to realize that we didn't know this. We had to wait a long time. We had to wait at least 50 years after Einstein's theory predicted them before we actually got observational evidence for black holes.
What's the event horizon?
The event horizon is the surface of the black hole. In other words, that's the region inside which you can't escape. Once matter collapses, basically all the matter collapses to a central point, of great density, but it leaves a region, a spherical region, which is called the black hole. And the edge of that sphere is called the event horizon. So when I talk about the sun collapsing to 3 kilometers, that would be the radius of this event horizon, okay? The radius is about 3 kilometers. Now, of course, and that's very small compared to the current size of the black hole, but however, it's 3 kilometers is quite large, it's just the size, it's the size of a little town. So that's really important, but it gets across the idea that you may have a prediction in physics, but you might have to wait a long time before you actually get observational evidence for it. So we had to wait 50 years before we had evidence for black holes. And in fact, we had to wait 100 years before we had evidence for the gravitational waves, which come from the merging of 2 black holes. I want to try and explain why this has such a strange effect on time. I explained how a gravitational field slows down time. Now, on the surface of the Earth, this is a small effect. It might be like a 1 in a million effect. So, the effect on your ticking of your clock is only like 1 in a million on the surface of the Earth. By the time you've got an object which is a black hole, it becomes far bigger than that. And in fact, what happens is that time stops altogether on the surface of a black hole. So let me try and explain this. Imagine that I am falling into a black hole, okay? You're watching me falling into a black hole. You're watching my clock. Yeah. As I approach the black hole, my clock is going to go slower and slower and slower. And then when I actually reach the horizon, my clock stops altogether. Yeah. Now, this is as an outside observer sees it. So if I'm waving to you as I fall into the black hole. I'm waving slower and slower and slower. And I get to the event horizon, I freeze. So from your perspective, Bernard has never fallen inside the black hole. He's sort of just frozen there on the event horizon. Okay. However, in my experience, and it's frozen because time, remember, runs slow in a gravitational field, and on the edge of a black hole, it stops altogether. In my experience, however, I carry on falling through the black hole, through the event horizon, I should say. Yeah. And I then carry on falling to the center of the black hole. Now, we don't quite know what happens there. Technically, there is likely to be a singularity in the middle of the black hole. And in theory, if I hit the singularity, I get destroyed. In fact, I get destroyed by tidal forces even before I get there. So basically, it's bad news if you fall into a black hole. You're going to get killed. However, for a big black hole, like the million solar mass black hole in the center of the galaxy, it doesn't have to be a great density. I mean, and you don't have to die when you cross the event horizon. For example, the density of the black hole when in the center of the galaxy would only be like the density of water. So the idea that your black hole has to involve huge densities, it's true if you're talking about the sun. The sun has to get to a huge density to form a black hole, but a supermassive black hole only has a relatively modest density. So you can carry on falling inside the black hole for quite a long time before you die in the middle.
Question.
Yes.
It's an insight that came up as you were talking about time slowing right down when you get to a black hole, like the idea of you waving slower and then you freeze. We spoke earlier about light and how at the speed of light, basically with a kind of timelessness, like you wouldn't see time moving at the speed of light. Correct?
The clock itself wouldn't appear to move.
Which is the same as you falling into a black hole, though. But it's diametrically opposed. One, it's like light isn't able to escape, so there's a kind of absence of light and time slowing right down. The other one, time is moving as fast as possible, and it's therefore not moving at all.
Let me try and explain.
Like the same
You,
situation.
you remember I referred to the light cone, you remember, first of all.
Yeah.
Now, in special relativity, the light cones, you remember, they're at 45 degrees.
Yeah.
Time is vertically upwards and space is horizontal.
Yeah.
What happens in the gravitational field is that the light cones, they bend over. Okay, so that instead of one light cone is going at 45 degrees to the right and the other is going 45 degrees to the left. But what happens as you go into a gravitational field, the light cones tilt. And so what happens is when you actually get to the edge of the black hole, the light cone, the outgoing light cone, is actually moving in the time direction. So it's parallel to the event horizon. The event horizon you see is at a fixed distance in space. It's a fixed radius. So that's like a vertical line upwards in this space-time diagram. And the outgoing light ray has also tilted to be vertically upwards as well. So the light cone itself is now directed inside the black hole. That's why light can't escape and nothing else can escape. The light cone itself has tilted so that it's actually going along the event horizon. The main point I'm trying to get across is that what's fascinating about black holes is that the effect of gravity on time becomes even more bizarre as possible, because your measurement of time as an outside observer is completely different from my measurement of time as I go inside the black hole. And indeed, as I fall inside the black hole, if I were to look outwards, I could see the whole future of our universe before I get killed at the central singularity.
Oh, well, okay, we'll come back to that in like literally 2 seconds. I just think it's a very interesting parallel, what you're talking about here with black holes and time. Yeah, and this temporal discrepancy between you as the person falling in and someone observing from the outside. And then to be in the position of a photon, like let's now pretend we're a photon. We're here on Earth and we are perceiving the light from the sun. As far as we can tell, that light takes 8 minutes or something, yeah, to travel from the sun to the Earth. The light itself, that photon isn't like getting on a little train and taking its 8-minute train to the Earth. It's everywhere all at once.
Yeah, a photon itself would experience no time.
That's what this is what I'm trying to say, and I think not everyone understands this. Like, I only know this because I was taught this. I never really thought about it before, to be honest, because we're taught about the speed of light, and then we're experiencing everything in this material domain where there are limits. Light has a speed limit, but the light itself is not limited. The light itself it's not experiencing time. It's simultaneous. It's everywhere all at once.
For a light ray, that's true.
Well, of course, a light ray, yeah, but I'm talking from the perspective of the photon.
Yeah, that's right. Now, of course, we're talking so photons are conscious beings.
I actually think they probably are.
That's getting more metaphysical still. But the point is, what is undoubtedly true is that from the photon itself, there is no actual passage of time.
From the perspective of a black hole, you'd be able to see the whole future of the universe.
As you fall through, if you happen to be looking outwards, in principle,
you'd be looking into the future.
The point I want to stress is that what happens for you when you fall inside the black hole is maybe even more interesting than what happens to the outside universe, because you don't really know for sure what happens to someone who falls inside a black hole. In the simplest picture, a nice spherically symmetric black hole got the event horizon, which is like a sphere, but then you've got a singularity at the middle. Now, the singularity, it's basically a point of infinite density. Okay. Unknown physics breaks down, but the idea that all the matter has compressed to an infinite density, forming this singularity, and then anyone who falls inside the black hole then eventually falls into the singularity and would die. However, we don't know what happens at a singularity because general relativity itself breaks down at a singularity. And so people now try and understand what happens at the singularity. And then you're in the domain of what is called quantum gravity, because quantum effects come in. However, the description I've given so far is for a normal, what's called a spherically symmetric black hole. It's much more interesting if, for example, the star is rotating. If the star is rotating, you form a rotating black hole. And then the situation is much more interesting, I suppose you would say, because the singularity is then like a ring. It's not a point, it's like a ring. And observers can actually avoid hitting the central singularity. And then the question is, what happens to them? Now, there are mathematical solutions in which you go through this, you pass through this ring, and you can go into another universe in some sense. And so this gives rise to the idea that rather than dying when you go into a black hole, you merely, it's like a portal to some other universe.
Okay, so that leads us on to the next nexus of questions or ideas, if you will. There's three things. I'm just going to break it down and then we'll go back over it. Three things are coming up for me. First of all, I wanted to ask you whether black holes could connect us with different dimensions, different timelines. Second of all, this, as we've spoken about, this theme of this episode and this seasonal arc is Kairos, yeah, which is distinct to Chronos being linear entropic time, Kairos being meaningful time. I wanted to explore the notion of black holes as potential kairotic apertures, so like an opening in time where we transcend linear time. And that could feed into black holes as portals. You just said black holes a portal going into an alternate dimension, alternate universe, and seeing the future of the universe. And then the third aspect of this constellation of ideas is about retrocausality and the notion of time being retrocausal. And the reason this is related is because I personally believe that Kairos, i.e. meaningful time, that synchronicity time, the magic time when you seem to be operating on a different dimension. There's a kind of transcendent numinous quality to it. I'm just wondering if black holes could be cosmic figurations of Kairos, like could be actual cosmological embodiments of a different opening of time, like a different kind of time. Does any of that make sense? That was quite nebulous the way I presented that.
I would say you're actually introducing two separate ideas.
Okay.
And I want to address both of them.
Okay. What are the two distinct ideas that you're seeing?
First of all, one could talk about black holes in terms of conventional physics and what Einstein's theory tells us about the behavior of physical objects in these extreme circumstances. However, when you're talking about Kairos, you're talking about something deeper. You're talking about experience. You're talking about consciousness.
Yeah.
And I will argue that there you have to go beyond relativity theory.
Yes.
You need to invoke a sort of deeper level of time. And so when you're referring to Kairos, I would claim that you're actually referring to this a different level of time, which doesn't actually itself come out of relativity, but it's the step beyond relativity. But let me first of all answer your question from the point of view of, if you like, relativity.
Yes, that makes sense.
I talked about the possibility that when you fall inside a rotating black hole, you could, in principle, go into another universe. And of course, that sounds fanciful. It sounds like science fiction. But anyway, the point is, this is a prediction of relativity theory, so it's not entirely fanciful. Of course, a lot of people will say we can't believe it because we don't really know what happens in the center of the black hole because known physics breaks down. But at least it's a possibility. But there are other things that happen inside a black hole, a rotating black hole. In principle, you have what are called closed time-like curves. Now, I should explain what they are. Normally, you remember I talked about the light cone and how we always have to move within the future light cone. And that, in some sense, forbids time machines, okay? Because if you're only going into the future, your motion can't go into the past. However, what happens is that you can have, in these solutions, you can go through time. You can, in fact, have the light cone itself moving over. You remember I gave a description with my hands about how the light cone can bend over under an effect of gravity. And in fact, at the event horizon, the outgoing light ray coincides with a vertical line, if you like. But now imagine that you bend it over even more. You can bend your light cone such that, in fact, the light cone can go through 180 degrees, which means that you can still be moving locally within the future light cone, but the future light cone itself is bending around so that you can have a path in space-time which goes back into the past and comes back to where you started from. This is rather hard to do without a diagram.
I know, because I've looked at this concept and I've looked at diagrams. It's actually quite easy to comprehend if you can see a diagram. Basically, like imagine like a bunch of a bunch of cones were all interlaced and going around in a circle, you'd get back to where you started. It's quite simple, actually. It's just hard to describe without a diagram.
But it is very mind-boggling, because what it's saying is that if there were light cones behaving like this, you would have what are called closed time-like curves.
Yes.
And they're called it's time-like because you're always moving into your local future.
Yeah.
And yet you're coming back to your starting point. You're going into the past. Now, the fact is there are solutions to Einstein's equations which permit this.
That's the grandfather paradox also. That would then mean
it leads to the grandfather paradox, because people say, well, you can't have closed time-like curves because then you can kill your grandfather before you're born. But however, that's simplistic, but nevertheless, that's the counter argument. And for that reason, quite a lot of physicists don't like the idea of closed time-like curves. Stephen Hawking, my PhD supervisor, he introduced what's called the chronology protection theorem. Something in physics must stop having closed time-like curves. You know, in principle, you have this possibility. And although someone like Stephen Hawking doesn't like this idea and says that something in physics must stop it happening, other physicists have liked the idea. And for example, Kip Thorne and colleagues, they were the first people to look at the possibility of these closed time-like curves. Actually, not the first people. There are other solutions of Einstein's equations. You have a rotating universe, which was studied by the great philosopher Gödel.
Yeah.
Gödel, and he showed that you could have closed time-like curves in these rotating universe models. But the point is, it happens within in this black hole context. And there's also something called a wormhole.
Yeah.
Now, a wormhole isn't quite the same as a black hole.
What's a wormhole?
A wormhole doesn't have a singularity, but it looks like a black hole from the outside. You go in through the mouth of the black hole, through the event horizon radius, but then you come out into a white hole. Everything goes into a black hole. Everything comes out of a white hole. So a wormhole has got two mouths, okay? And you go in one mouth and you come out the other mouth. Now, often you think of wormholes as short connections in space. So you've got two galaxies in space which are separated by millions of light years. So it will take millions of light years to get there. But a wormhole allows you to take a shortcut, if you like, through hyperspace, which means that you're able to go from this galaxy to another galaxy very, very quickly because you're taking a shortcut. So that was the first application of a wormhole. And that doesn't in itself involve a time machine. It allows you to travel faster than the speed of light.
Are they hypothetical? Are wormholes proven, or are they hypothetical?
No, they're purely hypothetical, unlike black holes, which are now well proved.
Okay.
But what it was realized is if you have a rotating wormhole, you can come out of the exit before you go into the entrance. Okay? And that is what Kip Thorne and colleagues studied. These rotating wormholes, if they were to exist, you would come out before you went in. And so that is why there is a link between time machines and wormholes.
And that's true retrocausality.
Well, now this is what's interesting, because then, of course, you're talking about retrocausality. Now, retrocausality is a reference to the fact that, in some sense, the effect can precede the cause. I mean, naturally speaking, remember, one of the arrows of time was the cause has an effect. Retrocausality says the effect can, in some sense, precede the cause, which sounds very counterintuitive. I mean, that's what a time machine allows. You, if you like, you are allowing what you're calling retroactive effects.
Yes.
This raises the whole question of the role of retroactive effects in physics. So this discussion is now going to go beyond black holes alone. The idea of retroactive effects has arisen in the context of black holes, but it arises more generally because so far we've only talked about relativity, but there's also quantum theory, and we haven't really talked about the role of time in quantum theory. That's another story. But quantum theory, just as relativity produces all sorts of weird effects, such as black holes, quantum theory is just as weird. Remember, quantum theory is the physics of the micro domain, whereas relativity is the theory of the macro domain. Now, there are all sorts of weird things associated with quantum theory. That objects are not described by wave functions, okay, rather than being localized, they're smeared out. You have the whole question of what collapses the wave function. Does consciousness collapse the wave function of an object? I toss a coin and it's heads or tails. we assume it's either heads or tails, but in quantum theory, it's a sort of superposition of heads and
both and.
tails
Yeah.
until you look at it. And once you somehow look at it, it collapses the wave function.
Yeah.
So that's one of the weird things about quantum theory. But the other weird thing about quantum theory is what's called entanglement.
Yes.
This may get a little bit complicated, but the point is that if I have an object, say I've got a system which produces two photons, one goes to the left and one goes to the right.
Yeah.
If I make a measurement, let's call them particles, okay, they've got some spin. If I measure the spin of the particle on the right, this is instantaneously going to determine the spin of the particle on the left.
Yeah.
And that sounds straightforward, but it goes against special relativity, because special relativity says nothing can travel faster than the speed of light. But no information can travel faster than the speed of light. But what is happening is that as soon as you measure the spin of this particle on the right, the particle on the left is instantly forced into the matching state. And that actually violates the principle of special relativity.
Well, it's instantaneous information transfer, isn't it, basically?
Instantaneous transfer of information. And so that is why Einstein himself was very reluctant to accept quantum theory. It's what's called the Einstein-Podolsky-Rosen, the EPR paradox. And so a big debate in quantum theory is, how do you resolve that paradox? There are different approaches. One is to invoke what's called non-locality, which is simply saying our concept of space breaks down. I mean, in some sense, our concept of time breaks down in general relativity.
Yep.
Time behaves very strangely. In quantum theory, our concept of space breaks down. So you have non-locality. You can't localize objects anymore. So that's incompatible with relativity, but nevertheless, that's what you need. Now, the reason I mentioned this is because some people think that one explanation of the EPR paradox and other quantum phenomena is that you can have retrocausal effects. Now, this is not definite because there are different views about this. However, there's what's called the transactional theory of quantum theory. And the transactional theory says that you in some sense, invoking retrocausality. Now, that's coming in a different context, but it's not inconceivable there is some connection between the retrocausality that could arise in the context of black holes and the retrocausality which could arise in the context of quantum theory. In fact, some people have even postulated that there may be a connection between wormholes, which arise in relativity, and this quantum entanglement.
Like micro wormholes, you mean?
In this case, it would actually be micro wormholes. We're not now talking about the sort of large wormholes associated with stellar collapse or supermassive black holes in the middle of galaxies. We're talking about a possibility of smaller black holes, or even what sort of something called quantum black holes. However, I have to make a caveat, because the transition from Chronos time to Kairos time is rather subtle.
Okay.
And I would argue that, in fact, when you're dealing with black hole phenomena, you are in some sense implicitly getting into the domain of Kairos time. These ideas, of course, are much explored in science fiction and movies. And for example, there's a nice movie called Interstellar, which you may have seen. And Interstellar involves going through a black hole. And in fact, Kip Thorne, who I refer to, he was involved in that. But what's interesting about it is that it's not only a wormhole. In Interstellar, if you remember the movie, he goes through the wormhole, but he goes back in time.
Yep.
And then, if you remember, he goes back in time and he's meeting his daughter, and he's in the library. And he's trying to move a book. Remember, to communicate with his daughter in the past. But the point was, there is a link there between the black hole and going back in time and memory and consciousness. Okay. So even that movie has introduced some link between, if you like, the black hole, which is a sort of astrophysical phenomena, and the experience of consciousness and memory. So even the black hole, this is a movie, of course.
Fine, though. Often fantasy belies a deeper mythic reality that is unseen.
Exactly. So I think, you see, your suggestion that a black hole in some sense is a portal to Kairos, I think that's true. But current physics does not describe consciousness. So when you talk about now, and when you talk about the passage of time, that is so fundamental to experience, it is not part of physics. Now, most physicists, and indeed most philosophers, conclude that, therefore, the passage of time is simply something to do with mind. It's projected by our consciousness, but it's not to do with physics. Physics is only to do with the third person perspective. It doesn't describe the first person perspective. And this is such an important point that even to describe consciousness, okay, you have to go beyond the relativistic description of time. How do you do it? The way I argue you do it, you have to invoke another level of time, which is, if you like, mental time associated with my mental experience. Okay. It's a second dimension of time, if you like.
Yeah.
And the point is, it's true that you can't describe the passage of time within the four dimensions of space-time, which is beloved of Einstein. However, by introducing this extra dimension, which, if you like, corresponds to mental time, you've got like a five-dimensional description of the world, and that can describe the passage of time.
Mm-hmm.
So what I'm arguing is that actually you need an extra dimension. You have to go beyond relativity theory in order to describe consciousness itself. Now, this shouldn't surprise you, because quantum theory and relativity theory, they are fundamentally incompatible. Relativity theory describes the macro world, quantum theory describes the micro world. They're incompatible. I've already explained how the entanglement is impossible in relativity. However, everyone accepts that the final theory of physics is going to marry up these two theories in some way. It's what they call the theory of everything. It's only a theory of physics, though. But what I'm going to argue is that when you've got your final theory, which marries relativity and quantum theory, that theory is itself going to incorporate consciousness and mental experience.
Well, it has to include consciousness because consciousness is the foundation of existence.
Exactly. That's my argument. I'm really trying to stress that I'm taking the view that the final theory of physics, and I have my own view of what that theory is, will accommodate consciousness and it will accommodate the passage of time. Because you see, it's all very well for philosophers to say, well, the passage of time is all in the mind. It's nothing to do with physics. But if your final theory of physics is going to accommodate mind and consciousness, it's got to accommodate the passage of time. Now, within my approach to this final theory of physics, a crucial role is played by higher dimensions. And in particular, one of those higher dimensions I'm associating with this higher dimension of time. And so what you might call mental time, okay, is this second dimension. I call it T2 as opposed to T1, which is physical time. Now, when you talk about kairos, you're talking about what, in my language, kairos corresponds to time too. One has to get into the distinction between chronos and kairos here. Chronos is dealing with physical time. Basically, it's something you measure. It's a measure of duration. Kairos time is of course much deeper. That's connected with how you interact with the world. You know, it's the moment of action. And so to me, that is actually what conscious time is. The passage of time is actually associated with this kairos time, in my view. And I have to say that in my own approach, it invokes higher dimensions. Now, higher dimensions arise anyway in physics. I've talked about the fourth dimension, which arises in special relativity. I've talked about the possibility of a embedding dimension, higher dimensional embedding, which describes general relativity. But also, we know the idea of higher dimensions has arisen in particle physics, because they're all the forces of nature, and it's realized that these forces of nature may also be associated with extra dimensions. For example, in the 1920s, it was realized that you could explain electromagnetism if there was a fifth dimension, another extra dimension of space. But this extra dimension is wrapped up very small on what's called the Planck scale, so you can't actually see it. But this mathematically explains the electromagnetic force. So it gives a geometrical interpretation to the electromagnetic force, just as Einstein gave a geometrical interpretation to the gravitational force. Now, people forgot about that for about 50 years, but then superstring theory came along in the 80s, And it was realized that you could invoke even more dimensions. In fact, superstring theory had 10 dimensions, okay? So you had 4 dimensions of space and time and another 6 dimensions all wrapped up very small. There were different versions of superstring theory, but then in the 1990s, it was realized all these different models of superstrings could be accommodated in what's called M theory. And M theory has 11 dimensions. So you've got 7 extra dimensions. And then there was one particular version of that which says you extend one of these dimensions, and then you see what we're calling the physical world is just a slice, a 4-dimensional slice in this 5-dimensional space.
Yeah.
The slice is called the brane, B-R-A-N-E, and the 5-dimensional space is called the bulk. And so in this picture, which is coming from physics, what we're calling the physical or material world, if you like, is just a slice in a high-dimensional, 5-dimensional reality, if you like. Now, that's coming from straightforward physics. What I argue is that all mental experience also requires a space, memory space, dream space, out-of-body space, near-death experience space, all requires a space. What you do is you marry up the idea of this high-dimensional mental space with the high-dimensional space of physics. You link them together.
Yep.
And to put it another way, if you believe the physical world is like a slice of a high-dimensional space, which is what physics is telling us, what else exists in that high-dimensional space? All I'm aware of is what's in my mind, my dreams, my out-of-body experiences, my hallucinations, a ghost, whatever. So the final theory, as I envisage it, is a higher-dimensional theory, okay, which accommodates both matter and mental and indeed even spiritual experience. So that's what my final theory is. And then the question is, what are these higher dimensions? In my theory, again, these higher dimensions relate to higher levels of time. I've already talked about the need for a second time, which is a description of consciousness. The final theory goes a bit beyond that because it says, well, actually, there can be different levels of time corresponding to different levels of consciousness. It's saying that the ultimate reality is mind-like, if you like. I want to bring in another point, though, before we run out of time. And that is, you can ask, what is the difference between Chronos time and Kairos time?
Yeah.
And it's very simple in a way. Chronos time is one dimension. It's linear, okay?
Yeah.
It progresses, okay?
Yeah.
But Kairos time is not progressive like that. It's more circular.
Spirals, would you say?
Well, it could be spiral, but the point is it's not linear.
Yes.
So the point is this higher dimension of time already contains the past and future of present time. So if you imagine space-time is 4-dimensional, a sheet of paper, the 5th dimension, the second time, that has the perspective which includes the past and the future. Imagine space-time is like a carpet, okay, of a tapestry of events. Your consciousness is able, in this extra dimension, is able to see the whole carpet, so it can see the future and the past. I think that's what memory is. And so from my perspective, Kairos time is this extra dimension, and that means it is implicitly part of this mental, this universal mind. Also, it's distinct from the linear time associated with normal physics. So everything I said in the first part of this talk was really to do with Chronos, physical time. But what I'm saying is that whatever the theory is, it must, I would say, accommodate consciousness, and it must accommodate what you were calling Kairos time.
Wow, what a beautiful place to close this absolutely fascinating conversation. Thank you so much, Bernard. There's so much, honestly, that's going to stay with me for days, and I think we'll have to percolate, and I'll keep contemplating because there's so much information that you've shared. Obviously, I'm looking at cosmology in my research, but I'm not a classically trained physicist. So it's really helped bolster, but through bringing your scientific expertise, it's helped bolster my philosophical understanding of time. I think we have a lot more to talk about. Probably, we should have another conversation at some point down the line.
We can have a wick rotation conversation later.
I'd love that. I'd love to talk about numbers and imaginary numbers. That would be amazing. Thanks for listening. I hope you enjoyed the show. If you'd like to go deeper into my work and find out about my offerings at the Temple, my School of Consciousness and Metaphysics, just head to my website, www.arabellathais.com, for more information, all the links in the show notes. See you next time.